All right, we are on to the next part of our exploration of the tangent function. The value of the tangent of an angle theta is the slope of the line passing through the origin and the point on the unit circle, cosine of theta, sine of theta, just like the diagram shows. So you can think of it as the slope of the terminal arm of angle theta in standard position. So here's that point, cosine theta, sine theta. And remember, this is sine theta, and this is cosine theta. And sine divided by cosine theta is your tangent ratio. We can also think of this as slope. That's another useful way to think about it. From the diagram, the distance AQ is equal to the y coordinate of Q. Therefore, point Q has coordinates 1 and tangent of theta. Okay. Thus, you can use the tangent function to model the slope of a line from a fixed point to a moving object as the object moves through a range of angles. First couple of examples here, we'll just do some review on some angles in standard position. The next couple of examples, we'll do examples where this thing, right? You can use the tangent function to model the slope of a line from a fixed point to a moving object as the object moves through a range of angles. And we'll show you, like in real time, or sorry, in real life, like what does that look like with the tangent function, okay? Note transformation. So for Math 30-1 here in Alberta, transformations on tangent functions are beyond the scope of this course. We looked at a few basic transformations like the b value, right? However, you must know the features of the basic tangent function, which was right here. All of this stuff is super useful right here. Okay. Okay, so you must know all that, definitely. You can also look at the reciprocal functions, cosecant, secant, cotangent on your calculator, but these will not be tested. Okay? All right, example 1. Also, this is also good. Do this on Desmos too. That's another great place to look. Okay, use one of those QRs that are provided from before. Okay, example 1. If point P 21 pi over 4, comma K is on the graph of y equals tangent of theta, then determine the exact value of K. This would be my x value, this would be my y value, or I think that is theta, and this is y. So when I plug it in, when I substitute y equals tangent of theta, y is k, and theta is 21 pi over 4. So we are doing this in radians, folks, okay? So when we think about this, we need to evaluate tangent of 21 pi over 4. Well, let's talk unit circle here, and let's do revolutions. The way I think about it is 20 pi over 4 is 5 pi. So I can go 5 pi in revolutions, right? And then I need to add how many more? Pi over 4 more to make 21 pi. Oops, let me just write it this way. And then, so I go 5 pi, then I go pi over 4 more, and that will be my 21 pi over 4. This is the way I like to think about it. So I start here. Here's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and I go pi over 4 more, which is halfway through the third quadrant. So this is my angle in standard position of 21 pi over 4. Okay, so in determine the exact value of k. So here I know that tangent is positive, right? So cast rule, C-A-S-T, so C-A-S-T in quadrant 3, the tangent ratio is positive, so I need a positive k value. Well, let's take a look at tangent of 21 pi over 4. That's negative square root of 2 over 2. So I'm thinking sine of theta over cosine of theta. Okay, sine of theta, the y value, that's negative square root of 2 over 2 divided by the x value. It's also negative square root of 2 over 2. And that just equals 1. So k equals 1. Example 2. Now let's take a look at a different example where I'm determining the angle from a tangent ratio, or the tangent function. If point P, theta, negative 6.2 is on the graph of y equals tangent of theta, then determine the measure of the angle theta to the nearest degree if theta is greater than 0 but less than 360 degrees. So, very important, we're in degree mode. Okay, so change your calculator to degree mode. So I have y equals tangent of theta. My y value is negative 6.2. And theta I do not know. I need to solve for theta. Okay, so remember, when we're solving for an angle, I need to take the absolute value of the tangent ratio. So this is what it looks like. Remember, I'm looking for theta r, reference angle, because this angle exists in more than just one quadrant. Okay, so reference angle equals, and you use the inverse tangent on your calculator, absolute value of negative 6.2. And then my reference angle I get is 80.8376 degrees. It says to the nearest angle. We'll round at the very end. Okay, so I'm just showing you a bunch of significant digits here. Tangent of theta is less than 0. Okay, so that's negative. So I'm going to look for where tangent of theta is less than 0. That's in quadrant 2. Okay, so in quadrant 2 or quadrant 4. So in quadrant 2. There's my theta r value, so angle in standard position is 180 degrees minus 80.8376 degrees. And so my angle in standard position is 99 degrees. In quadrant 4. There's my theta r value. Angle in standard position there is 360 degrees minus 80.8376 degrees. And that equals 279 degrees. Okay, example 3. Let's do an application problem involving the tangent function. A small plane is flying at a constant altitude of 5,000 meters directly toward an observer. Assume the ground is flat in the region close to the observer. Determine the relation between the horizontal distance in meters from the observer to the plane and the angle in degrees formed by the vertical and the line of sight to the plane. Okay, so let's think about this. The plane, so here's the observer. And constant altitude of 5,000 meters, so $5,000 meters. Okay, flying towards an observer. So here's my plane. And then here's the line of sight from the observer to the plane. And by definition, from the example description here, we'll call that theta. This is a right triangle. And so we've defined this distance as x. Right? So if I do my tangent ratio, let's get our tangent function, our equation here. Tangent of theta is opposite over adjacent is x over 5,000. Okay? So x equals 5,000 tangent of theta. Let's actually, to make it less confusing, let's call this y, because when we graph this, it'll make it less confusing. Okay, so I'm going to say, oops. So if I start over, folks, I'll call that y. So tangent of theta equals y, opposite over adjacent, 5,000. So y equals, this is our tangent function, 5,000 tangent of theta. So that's my a value, right? This is my vertical stretch, a value. Sketch the graph of the function. So let's take a look at this. So I have my function y equals 5,000 tangent of theta. I'm going to plot a couple of key points here. Theta equals 0. Tangent of theta. Let's do a chart here, folks. Theta and y. Okay. At theta equals 0, tangent of theta is 0. Okay, so remember we're in radians here, so y is 0. Okay. Let's do a couple of other key angles here. I'm going to do pi over 4. And I'm going to do negative pi over 4. Okay, so pi over 4, tangent of pi over 4 is 1. So my y value is 5,000. And tangent of negative pi over 4 is negative 1. So tangent of negative pi divided by 4 is negative 1. So I have negative 5,000. Just means 5,000 in the other direction. So pi over 4, 2, 4, 6, 8, 6, 5,000 right about there. And then pi over 4, 2, 4, 6, right there, 5,000. Okay, a couple other key points that I'm going to do is, let me just do 2 more here. Pi over 2. What happens at tangent of pi over 2? Well, that's undefined, right? What happens at tangent of negative pi over 2? That's also undefined. So what do I have there? I have asymptotes. So let me draw on some asymptotes, folks. Asymptotes. And let me draw that in blue. Okay, at pi over 2. No, come on. I need asymptotes. And at negative pi over 2. Okay, and then I know it's every pi over 2 units, we're going to keep having asymptotes. So I'm going to do another set of asymptotes at 3 pi over 2. And then another set of asymptotes over here at negative 3 pi over 2. Okay, there we go. And then so we know this tangent function is a repeating function. So if it looks like this in this section, it's going to look the same in the other sections as well. So I'm just going to repeat it like that. Oh, let me fix that. That's not correct. Let me fix that, folks. Right there. Yep. And this side. Okay, so that's our tangent function. All by putting a couple of key points. Okay, so this is good review on how to graph these. Identify where the asymptotes are located in each graph. Explain what they represent. So we've showed you why the asymptotes are where they are. So these are asymptotes, right? Because that's where the tangent function is undefined. Well, let's take a look at this logically on why that is by drawing some diagrams here. If I have a very small theta, and I make the theta progressively bigger, right? Let's make it a little bit bigger. And let's make it even bigger. Even bigger, like that, right? This is, remember, this is the plane as the plane is approaching, right? As the plane is approaching, as theta increases, here's my x value, folks. X. What's happening to my x value as theta increases? As theta increases, x gets bigger and bigger. And then as theta, when theta equals pi over 2, well, how can I draw that? Well, take a look. Here's the observer, right? Here's the vertical distance. And here's the x value. I'll do this. For a theta of pi over 2, well, that's what this looks like. Theta of pi over 2. How can I have a triangle, right? We said that the airplane, has a vertical height of 5,000 meters. But for a theta equals pi over 2, what happens? This x value oh man, sorry. I should call it y value. I should be consistent. Remember, I changed these all to y values, that horizontal distance. Sorry about that, folks. So this is that y value, because that's what I called it here and here, right? And here. Okay, so this y value is undefined. Okay, so that y value is undivided, and that's what we saw here and here. Okay. Where are the asymptotes located? So the asymptotes are at on the graph, right? So what we can see, negative 3 pi over 2. So in units of pi over 2. So negative pi over 2. Sorry. It's pi over 2 separated by units of pi. So I'll show you the general form here. So on the graph, these are my asymptotes. Or generally, my asymptotes has the equation x equals, well, we know it's pi over 2, plus it varies every pi units times n, where n is an element, of integers. Okay? So the general statement I can think of is I'll write it up here. At theta equals pi over 2, the plane cannot remain at 5,000 meters. And then we show that with this diagram here. Okay, so letter D, explain, next one, explain what happens when the angle is equal to 0. So we can draw another diagram here. Oops. So as the plane gets closer and closer, so let's start at theta, a very large theta value. Here's my airplane. Okay, here's the observer. As theta gets smaller and smaller, this is my y value. Here's my airplane again. Here's my y value. Here's my observer. And let's make theta a really, really small angle. Oops. Here's my plane. So what's happening? As theta approaches 0, so as theta gets smaller, the plane's horizontal distance decreases. Okay, or in other words, it gets closer. So as we go from here to here to here, theta gets smaller. Okay, theta goes down, theta goes down. The plane gets closer in terms of horizontal distance y. Okay, plane's horizontal distance y. When theta, the angle equals 0, Well, what happens when it's 0? It's no longer a triangle. And physically, what's going on? When theta equals 0, the plane is directly overhead. The horizontal distance. So what is the horizontal distance? Remember, it gets smaller and smaller as theta decreases, right? Well, what is the y value here? Well, y value equals 0, right? When the plane is directly overhead. So when theta equals 0, the plane is directly overhead. The horizontal distance, is y equals 0. Y equals 0 meters. And we saw that from our equation. Y equals 5,000 tangent of theta. So if I plug that in, y equals 5,000 tangent of 0. That's a y value equal to 0 meters. And we can see that up in our graph right here. Right there. Theta equals 0, y equals 0. All right, ready for a challenge here. A security camera scans a long straight fence that encloses a section of a military base. The camera is mounted on a post that is located 5 meters from the midpoint of the fence. The camera makes one complete rotation in 60 seconds. Determine the tangent function that represents the distance d in meters along the fence from its midpoint as a function of time t in seconds if the camera is aimed at the midpoint of the fence at t equals 0. All right, so let's just sketch this out. If I'm looking from overhead, there's my security camera, right? And it has a view as it sweeps out its angle, right? So it starts here, then goes around quarter cycle, half cycle, 3/4 cycle, full cycle, right? So this security camera is rotating at a constant rotational speed, and it is filming or videotaping whatever's going on in this military base, okay? So that's the physical reality, what's going on. It says one complete cycle in 60 seconds. So one cycle in 60 seconds. Okay, so remember for a tangent function, if I go back, I'm just going to go back here real quick, folks. This one, all the way back here. The tangent function, one period of the tangent function is pi radians, or 180 degrees, right? So it's pi radians. So when we go back and think about our b value, we have to be careful here, right? And we have to think in terms of, for a tangent ratio, we have to think in terms of half cycles, right? So one cycle, so this is one full cycle. This is one full cycle. A tangent function, one cycle, is actually pi radians. So if this is one full cycle all the way around, this is 2 pi radians, right? I have to think of 30 as my half cycle equals, remember for tangent it's pi over absolute value of b. If this were a sine function, we would do 60 equals 2 pi over absolute value of b. But this is not a sine function, this is a tangent function. So my b value is therefore pi over 30. When I do my tangent function here from this snapshot, I have my distance d along the fence line, 5 meters, and I'm going to call this time. Okay, and then let me do this first and then I'll explain why I'm using time instead of theta or an angle. So I have tangent of b theta equals opposite d over adjacent 5. Okay, but instead of theta, I'm going to use time t. My b value is pi over 30 times time equals d over 5. Let's write it in terms of d, that distance across the fence line. That's d equals 5 tangent of pi over 30 times t. So when I think of the camera here, see, this is 15 seconds. 15 seconds. 15 seconds. 15 seconds. Okay? Also, pi over 2 radians, pi over 2 radians, pi over 2 radians, pi over 2 radians. We assume, like most cameras do, assume the camera moves at a constant rotational speed. Rotational speed. Okay? Therefore, time is proportional to angle. That's why I'm using time instead of an angle here. They are interchangeable. They are directly proportional. Okay, so that is why we're using t, not a theta value. Okay, so the first part, determine the tangent function. Here's my tangent function. Next part, let's graph it. Let's graph it in the domain -15 to +15. So when I do this, this is roughly what I have here. Okay, this is my telltale tangent function here. Okay, what is the distance from the midpoint of the fence at t equals 10 seconds to the nearest tenth of a meter? So when I look at this, folks, d equals 5 tangent of pi over 30 t at 10 seconds. I get a d value of 8.7 meters. Okay, so let's map that on here. So roughly about here, 10 seconds. So this is t, this is d. This is 8.7 meters. Okay, so that's that value there. Let's see. Describe what happens when t equals 15 seconds. Okay, so let me draw a series of triangles here. So when I start, there's my theta value, or let's think of it in terms of, time or theta. Okay, and this is d. And then here's my camera. And then as t gets bigger, what happens? This is my camera. As t increases, right? Let's make t really big here. This is my camera. Okay, as t increases, d also increases. Okay, but if we think about it this way, I'm going to draw the fence here. Here's my fence. Here's the camera. Let me split it up into sectors of 15 seconds or pi over 2 radians. So this is 15 seconds, 15 seconds, 15 seconds, 15 seconds. So when the camera's pointing here and it keeps going this way, what happens to the d value? Well, the d value keeps going up, but when I have the camera pointing this way, what is the d value? So as t approaches 15 seconds, the d value, the distance across the fence, approaches infinity. So I can show that with my equation. D equals 5 tangent of pi over 30 times 15 seconds. So that's D equals 5 tangent of pi over 2. Well, we know that pi over 2, that's undefined. So therefore my D value is undefined as well. Well, we can see physically why, because D gets bigger and bigger as t goes up. So when we point this way exactly at 15 seconds, right, we're going to have an infinite value, or the d value doesn't exist. Okay? And then if you map this out, t versus d, I did this for a couple of values. When t equals 1 second, the distance across the fence is 0.52 meters. At 3, it's 1.62. Okay, on and on. At 11 seconds, the distance is 11.23. At 14 seconds, the distance is 47.57. And then as you get closer and closer to 15, these values skyrocket, they go up. So 14.5, 95.41 meters. Let's go to 14.9. 477.44 meters. Let's go to 14.95, even bigger, 954.92 meters. Let's go to 14.99. You get the idea. I get 4,774.65. Okay, so that's what happens as when t equals 15 seconds. So as t approaches 15 seconds, d approaches infinity. This means the camera is pointing more and more away from the midpoint of the fence at t equals 15 seconds. The camera is pointing along a line parallel to the fence. and I'll highlight it. That's what it would look like right here, parallel to the fence. Okay, so that's what we're seeing physically, and we're seeing it through this progression here.